Bueno, es el turno ahora de Alba Hidalgo, del Departamento de Microbiología.
Well, good afternoon. I'm glad to be here today talking about my work and learning more about the work of other people here in the Estación Experimental. I've been working in the nitrogen metabolism group for 10 years now, but it's only really recently, in October this year, that I started my PhD. That will be delineated by this project, Emisión de óxido nitroso por suelos cultivados con leguminosas y hortalizas de interés agrícola, and titled Emission of the greenhouse gas nitrous oxide by Phaseolus vulgaris, Rhizobium, etli, simbiosis. Phaseolus vulgaris, colloquially known as the common bean, belongs to the legumes, a big group of plants with high economical and nutritional importance around the world. One of the main characteristics is the ability to establish symbiotic associations with soil bacteria called Rhizobium, leading to the formation in the root of new structures, the nodules, where bacteria become bacteroids that are able to fix molecular nitrogen, atmospheric nitrogen, to ammonia through the nitrogenase enzyme activity. This biological nitrogen fixation by this symbiosis, it's an economical and environmentally friendly practice to increase soil fertility and crop yield without adding nitrogen fertilizers. However, legume nodules also are potentially capable of producing N2O and NO through rhizobial denitrification. N2O, it's a powerful greenhouse gas due to its high relative potential and its high stability in the atmosphere. About 60% of this gas comes from agriculture. Nitrogen fertilizers and organic matter coming from the farming lands provide with nitrate and ammonia substrates for nitrification and denitrification, the two main microbial processes that contribute to the emission of nitrous oxide. Well, as Lady said before in her presentation, there's always a good guy and a bad guy in the films. In this case, the same guy has a good part and a dark side, because Rhizobia are able to fix nitrogen from the atmosphere and give it to the plant. So this is proposed as like a strategy to decrease our dependence on nitrogen fertilizers that are contaminant to our environment. But at the same time, as I said before, these nodules are able to produce N2O. So it's important to understand how the nitrification process is regulated and which are the factors that are involved in this nitrous oxide emission. Under low oxygen conditions, some bacteria are able to use alternative ways of respiration, like denitrification. This pathway is very good, is well known in the model bacteria Rhizobium diazophycins. It consists in a sequential reduction of nitrate to nitrite, nitric oxide, nitrous oxide, and finally molecular nitrogen, in 4 steps catalyzed by the enzymes periplasmic nitrogen reductase, alpha-containing nitrogen reductase, C-type nitroxide reductase, and nitrous oxide reductase, encoded by the genes NAP, NIR and NOS respectively. But other bacteria, like the bacteria we are studying this work, have an incomplete denitrification pathway. The Rhizobium LCFM42 genome lacks the genes encoding for the periplasmic nitrous reductase and the nitrous oxide reductase. So the general aims of this work will be to investigate the ability of Rhizobium LCFM42 to produce N2O under free living conditions or symbiotically associated with common being plants. To study the genetic factors involved in N2O emission by Rhizobium etli, and to determine the involvement of environmental factors such as pH, the copper availability, carbon source, or water stress in N2O emission by Rhizobium etli. In reference to the first objective, the first thing we did was to check if this bacteria is able to produce N2O. Interestingly, by gas chromatography, N2O production was detected in the headspace of cultures of the wild-type strain, grown under low oxygen conditions and nitrate as the only nitrogen source. By contrast, this is wild-type, by contrast, cells of NIR-K and NOS mutants were unable to produce N2O. To explain the production of N2O in a bacteria that lacks the gene encoding for the respiratory nitrate reductase, we propose that the nitrate from the media is reduced by an assimilatory nitrate reductase to nitrate. And this nitrate is exported to the periplasmic space, where it's reduced by the NIR-K enzyme to NO, which in turn is reduced by the NOS enzyme to N2O. In fact, when ammonia was present in the medium, N2O production was significantly inhibited in the wild-type cultures. This makes sense, since it is known that ammonia inhibits the pathway, the nitrate assimilation pathway. So these results lead us to suggest that Rhizobium etli produces N2O by coupling nitrate assimilation pathway to denitrification pathway. Finally, I would like to thank all my colleagues from my research group, especially my direct supervisor, Maria Jesús Delgado, and I also appreciate collaboration of Lourdes Gerard from the Center for Genomic Science from the National University of Mexico. And of course, thank you all for your attention.
The hypothesis is very interesting. Do you plan to make a mutant in the... Do you plan to make a mutant in the nitrate reductase to confirm that it is the gene involved?
I mean it already. I can say that I almost have the mutant. I have it, but I have to check it. But it looks very, very good. I think that will confirm the hypothesis.
Another question. So you see that when you add ammonium as the salt nitrogen source?
Well, in this business, salt is double.
Okay.
Because without nitrogen, we wouldn't be production of any oil as well. But when ammonia, sorry.
So if instead of ammonia, you used, for example, amino acids as nitrogen nitrogen sources,
I haven't tried that.
what would you expect? Would you expect also reduction?
No soy nada. Yo estoy un poquito sorda hoy, pero...
Estoy un poquito afuera.
Sí, perdón.
La pregunta es si usando aminoácidos como fuente de nitrógeno en vez de amonio, esperarías también una reducción en la producción.
¿Hasta qué punto si la bacteria es capaz de utilizar solamente incorporado directamente en las proteínas? Seguramente sí, porque la cuestión es que para la bacteria no es dificultoso incluso utilizar el amonio. Entonces, obviamente si tiene amonio lo vamos a utilizar primero.